Hello, and welcome everyone to PyData Boston's December Meetup. For those of you who don't know, PyData is an educational program of a nonprofit organization called NumFOCUS. The global PyData network promotes discussion of best practices, new approaches, and emerging technologies for data management, processing, analytics, and visualization. We are a community of users and developers of open source data analysis tools, and this meetup is a forum for us to share ideas and learn from each other. We also approach data science using many languages, including, but not limited to, Python, Julia, and R. My name is Anita Yip, and I'm one of the co-organizers of PyData Boston. We're really thrilled to have two presenters for you tonight. First, we'll hear from STANLEY ZHENG, providing a comprehensive guide on the applications of pseudolabeling and how he won a Kaggle medal using only pseudolabeling. Afterwards, HARINI KANNAN will go through topic modeling for data discovery and focus in on a cybersecurity use case. Now, before we get to them, I want to touch base on a few items. First, feel free to introduce yourselves in the chat and in Slack, where there's also an introductions channel. As we continue to hold virtual events, we want to continue building our community. And of course, if you have questions during the presentation, please unmute yourself and chime in for a real-time conversation. And for those of you who aren't speaking, just please make sure to turn off your microphone. And we have our website up at boston.pydata.org and on social media. Feel free to tweet about today's talk using hashtag PyDataBoss. And if you haven't joined our Slack community yet, please do. This information is also on our Meetup page. As of all meetings, we want to reiterate that PyData is dedicated to providing a harassment-free event experience for everyone. Please behave professionally, as we do not tolerate harassment in any form. You can view the longer version of our code for conduct at this website, so feel free to reach out to any of the organizers if you have concerns. Thank you again for helping to make this a welcoming, friendly community for all. And lastly, these meetings are only made possible with the help of volunteers. You can do anything from organizing an event by recruiting speakers to creating partnerships. When we're back to meeting in person, you might also help secure venues and food. What's more, we have an ongoing need for speakers. Please consider volunteering to present and speak at one of our meetings. You don't have to have a full talk ready when you fill out the speaker form, as the organizing team can help you through that. And in fact, Harini was someone who filled out our speaker form, so I'm excited that we were able to connect and have her present tonight. We're really in for a treat from both speakers. And with that, I will turn it over to Stanley.
Okay. A guide to pseudolabeling, how to get a Kaggle medal with only one model. Privacy has been a hot topic on the news, whether this be a smart speaker recording constantly or a social media app turning on your camera in the background. With this comes the question, where does all of this data go? There are thousands of hours of recording, and that can't really be hand labeled. For Amazon Alexa, and possibly hundreds of other companies, all of this data is pseudo-labeled. According to a blog post in April, Amazon uses this technique to help Alexa match skills to customer requests. And this technique, pseudo-labeling, is the topic of today's talk. A bit about me. I'm Stanley, a student at Athabasca University from Alberta, Canada. I love the field of data science and machine learning. I'm a Kaggler, and my interests include photography, computer vision, and fintech. I'm an open source contributor on a few repos on GitHub, as well as a few hackathons, which is where I met Anita. You can find me on GitHub, Kaggle, LinkedIn, and DevPost as @StanleyZHENG. In my first Kaggle competition in June, I placed 73rd out of 2,245 competitors, which is in the top 3%. The catch is that I achieved this in 2 weeks using one model, while most, if not all, top teams used an ensemble of 2 to 5 models and had a period of 3 months. Today's talk is about some of the tips and tricks I've learned, a guide including validation techniques, examples, when to apply pseudolabels, and when not to. First, we'll talk about what pseudolabels are and how and why anyone would ever use them. Next, we will talk about how to effectively use pseudolabels, including training and validation schemes. Thirdly, we will talk about applications, specifically a few Kaggle competitions and the previous state-of-the-art image classification model on ImageNet. And finally, I have a simple demo in TensorFlow and Keras on the MNIST dataset. I'll mostly be discussing the application to neural networks and deep learning today, or machine learning in general. And I've created a small list of further reading and references in a GitHub repo, which you can find at bit.ly/PyData-GitHub. This link can be found in the bottom left corner of every slide, and the slides are also uploaded there. Special thanks to Johan Babakin for providing some of the graphics and results of pseudolabeling from competitions. His paper titled Semi-Supervised Segmentation of Salt Body of Seismic Images Using an Ensemble of Convolutional Neural Networks is referenced in the GitHub and provides an excellent look into the full process of a winning team in a Kaggle competition, including pseudolabeling. Let's begin by exploring what pseudolabels are. Pseudolabels are a form of semi-supervised learning. Semi-supervised learning means that you can leverage a small labeled trained dataset and a large unlabeled dataset. Semi-supervised learning takes elements from unsupervised learning and supervised learning. Some techniques that fall under this umbrella include adversarial methods, but pseudolabeling is the most simple and the subject of this talk. So what is pseudolabeling and how do you use it? The basic ideas of pseudolabeling are quite simple. First, we train a model on our labeled trained data. This is the supervised learning part. Then we infer on the unlabeled data. These inferred labels are now called pseudolabels. Now, after merging the original labels alongside our pseudolabels, we can retrain the model or train a different model on the new set containing pseudolabels. This is unsupervised learning. In this way, your training data is not only your labeled data, but also your unlabeled data. When I learned this technique, it was quite unintuitive. Since the model made the predictions that were used to train itself, doesn't it already know the information, and wouldn't this propagate error, reinforce class imbalance, and overfit? However, through training augmentations and dropout, the pseudolabel model will almost always outperform a model without pseudolabeling, and is probably more robust also. Here's a graphic to demonstrate. This is a simple classification problem between the blue squares and green triangles. With labeled data, we can just draw a decision boundary with supervised learning and classify them based on the labels. Next, we can introduce some unlabeled test data, let's say red circles. However, if we were to just use this model with our decision boundary, we would cut through some of the red circles and it'd be incorrect. So this is where we can label the red circles and we can pseudolabel the red circles so that we are training on the red circles. And so our final model would be something along the lines of this. With pseudolabeling, we can also utilize the unlabeled data shown in red circles. Though we did not change the labeled data, we can see that with the introduction of the unlabeled data, our final model is significantly different, more robust, and more representative. The introduction of the unlabeled data has positively changed the way our model performs. So why would you want to use pseudolabels in the real world? There's a few reasons. Firstly, data is expensive to label, either difficult to obtain or difficult to label without a large workforce. For example, you're labeling hundreds of heads of wheat in one image, so it's infeasible to hand label all of them. Or maybe you're classifying CT scans and need a domain expert or radiologist to label it for you. Another reason is that data is time-consuming to obtain or label. Models need to be made soon, but time is needed to build the training set and label it. Alternatively, data needs to be sorted to be used. The data diversity could also be inadequate. For example, if we are taking images, the training images could be from one location and the test location with different lighting, species, or something along those lines. And really, pseudolabeling can be applied to any application where there is very little trained data, but a lot of unlabeled test data comparatively, so that we can leverage this test set for better performance. An example of this would be the ImageNet dataset, where 14 million images were assembled and hand-labeled in over 1,000 classes, and it took 7 years to construct. However, 350 million photos are uploaded daily to Facebook, weekly sorted by hashtags, according to a white paper by Facebook in 2013. These images are probably more diverse than any pre-made datasets. And if we can effectively leverage these massive amounts of data, then our models will perform significantly better. So that's the basic idea of pseudolabels. And while the general idea is quite simple, there's a wide variety of popular implementations. I'll discuss some of these popular implementation techniques for training first, and then validation, and some general tips for a successful implementation. Training has a few popular schemes. All of these start the same way. We train a model on the labeled data and then infer pseudolabels, but the way the pseudolabels are trained on differs. First, we have the most simple, self-training. In self-training, a model which is already trained on labeled data is then used to infer on unlabeled data, then fine-tunes itself with pseudolabels that it itself creates. This is usually the least performant method to train pseudolabels, but is by far the simplest, only requiring one single model and some copy-pasting of inference training code. This scheme also sometimes propagates error and is usually sensitive to hyperparameters compared to the others. Our second method is simultaneous training. Simultaneous training is when pseudolabels are mixed with the labeled data, then trained simultaneously. So the full end-to-end would be, we train a model on the labeled data to produce pseudolabels. And then we combine the labeled data with the pseudolabels to form a larger labeled data set, which we then train a new model on. The model that is trained can either be ImageNet pre-trained and then fine-tuned in the new combined data, or model initialized from scratch. However, with this method, you may want to train from scratch rather. Our third method is to pre-train the model on pseudolabels alone. So after obtaining pseudolabels from your original model trained on labeled trained data, instead of using pre-trained weights from, say, ImageNet or other pre-trained weights, we train our model and pre-train it on pseudolabels. So, and the idea behind this is that the weights from the model trained on pseudolabels are going to be much more representative than the actual pre-trained weights from ImageNet. And this method is described more in a paper titled Native Semi-Supervised Deep Learning Using Pseudolabel, where the authors achieved significant performance improvements using pre-training with pseudolabels compared to an ImageNet weights initialization. This is an extremely impressive technique in which, with only 100 training samples, their MNIST model achieves 75.5% accuracy on 28,000 image test set, which is, with only 100 training samples. There's also a few things to keep in mind with pseudolabels. These are a few guidelines that I've picked up and are shared around Kaggle and sometimes around papers. Firstly, pseudolabels need to be applied to data, which is at least somewhat representative of your labeled trained data. If your model encounters an edge case or out-of-domain data which is not addressed by training data, it's not likely to guess correctly. So your pseudolabels are of low quality and noisy. However, if your data contains a reasonable number of out-of-domain elements, you may be able to filter it through confidence. For example, you may only choose a pseudolabel if one class is over 80% certain, so out-of-domain data is hopefully excluded from your pseudolabels. In general, your pseudolabels will be more effective if you filter pseudolabels to confident predictions only. Secondly, soft pseudolabels almost always perform better than hard pseudolabels. Hard pseudolabels mean that there's no confidence interval, for example, just a 0 or a 1 in a classification problem. Soft pseudolabels have a confidence for each class. So for example, 0.1 for label 0 or 0.9 for label 1. And training on soft pseudolabels will give better performance as it approximates the model that the pseudolabels are produced from. But soft pseudolabels are not always possible to create or train on. Thirdly, we can reduce pseudolabel variance using Ensemble. It is crucial for pseudolabels to be accurate for a good pseudolabeling implementation. And in addition to the techniques mentioned above, we can add Ensemble. It does not necessarily have to be different models. For example, if we're doing computer vision, we can use TTA, test time augmentation, where we can flip an image, infer, maybe change the brightness and infer again, or maybe K-folds as a viable option to Ensemble without the hassle of engineering multiple model architectures. An ensemble of different models to produce pseudolabels will result in significantly better quality pseudolabels and will pay dividends during training. I'll talk a bit more about ensemble models later on. Finally, we will most likely need to use multiple rounds of pseudolabeling. For pseudolabeling to be effective, it usually needs to be iterative, not one shot. After each iteration, we can add pseudolabels that the model is most confident on, or even ensemble predictions with the pseudolabels from the previous iteration. Iterations of pseudolabels are also likely to be more robust and performant than the previous iteration. In fact, the state-of-the-art ImageNet model uses many iterations of pseudolabels, up to 5. It is worth noting that when using multiple rounds of pseudolabeling, we must initialize the model weights after each round. So you cannot simply use the same model to train on pseudolabels, create pseudolabels, train on pseudolabels again. We have to train on pseudolabels and then create a new model initialized from weights from ImageNet, or else we would have quite ridiculous error propagation. In every other respect, though, pseudolabels can be treated like normal labeled training data. For example, class balanced datasets generally perform better, or we can use class balancing like SMOTE, synthetic minority oversampling techniques, and the model will be made more robust through augmentations and dropout. Pseudolabels benefit especially from augmentations, dropout, and stochastic depth, since they allow the model to be more robust than the model that initially produced them, which is especially important during self-training. Validation is another common trap. In Kaggle, you may overtune to the leaderboard, or in the real world, you may overtune to your validation data. I'm not sure if this is used too much outside of Kaggle, but in Kaggle, most validation is done with k-folds. K-folds is robust, along with being very easy to incorporate into pseudolabeling. Here's the gist of what k-folds is without pseudolabeling. First, we shuffle the dataset randomly. Next, we split the dataset into k groups. Usually this is about 4 to 10 groups. Now for each group, we take it out and do not train on it. It is our test set. We take the remaining groups and train a model on them. Finally, we evaluate the model on the withheld test set. We can repeat this for k-folds, which is where the name comes from. This validation is so effective because it allows us to train on our entire dataset, yet have extremely effective and unbalanced validation. There are multiple ways we can use pseudolabels alongside k-folds. The most obvious way is to simply train a model for each fold and then ensemble their prediction into one set of reliable pseudolabels. However, this is a slightly leaky approach. If we decide to validate our model in pseudolabels, then the evaluation data comes from the predictions from our model. Therefore, it would be too optimistic and the cross-validation would be unrealistic. We can see this more clearly in the graphic. For each fold, we have a single fold of pseudolabels that the model already trained on. Therefore, the pseudolabels produced for validation would be higher quality than any realistic test data. Another option is to train each fold and then evaluate the pseudolabels separately and train on the pseudolabels separately. Then each fold can be trained on its own pseudolabels and evaluated on the same k-folds test data afterwards. This is a very reliable, non-leaking method to evaluate pseudolabels on each fold. However, this leaves a lot of performance on the table. Instead of ensembling our k-models, we're evaluating them individually, so our pseudolabels are less likely to be accurate, probably noisier, and more variant. As we can see in this graphic, each fold has its own set of unique pseudolabels, and so this method is not leaky at all. Nevertheless, the evaluation scheme chosen by most Kaggle winners is slightly leaky. There are certain reasons to choose a leaky validation, however. Let's say we have 4 folds per model. These 4 folds are quite diverse, so it's meaningful to ensemble them. Let's then say we have 3 model architectures, which is reasonable for a competition lasting a few months. Then we already have 12 model variants to ensemble for one single set of pseudolabels, rather than 12 individual, lower quality sets of pseudolabels. This way, though the validation is slightly leaky, the benefits of an ensemble of many diverse models producing pseudolabels together greatly outweighs the importance of having a single, more correlated cross-validation. It's also possible to use the non-leaky cross-validation to evaluate models, then train the final approach with a slightly leaky cross-validation. As with most machine learning applications, depending on data, there are many hyperparameters to adjust and many schemes that may or may not work. We can make cross-validation less optimistic by excluding pseudolabels from the validation folds. For example, we can get the labels, run the k-fold on only the original labeled data with real labels, and add the labels to train exactly at training time. This way, our cross-validation isn't biased by easy and artificially noiseless targets that were produced by another model. We could also try adding some noise to the pseudolabels, for example, randomly flipping labels as in the data generation process, as another way to combat overfitting and create a more reliable cross-validation. There's a ton to experiment with when it comes to pseudolabels, and there isn't really one correct formula. Now that we've discussed some of the main applications of main elements of pseudolabels and their implementations, I'll go through some applications. Firstly, we will explore some of the solutions of a recent Kaggle competition. For those who don't know, Kaggle is a data science community organized by Google. We have competitions with a prize pool of up to $1 million, and anyone on the internet can participate. The competitions work this way. Individuals submit models, which are evaluated on a public test set, which we can see whenever a submission finishes, and a private test set, the final score of the competition, and released at the end. We get to pick 2 final submissions to run on the private test set, and the better score is the one at the end of the competition. However, there's a few tricks. Usually the training set is relatively small, and there are commonly some tricks in the test set. This particular competition was called Global Wheat Detection, made by the University of Saskatchewan. This used computer vision, specifically object detection, to identify wheat head size and shape from an image. To work with, we had about 3,000 train images, around 1,700 public test images, and 800 private test images. So this was quite a small data set for object detection. The trick with this competition was that there was a new location in the private test set with different variants of wheat. For example, the train test set used wheat from Saskatchewan in Great Britain, while the private test had some wheat coming from Japan. With this and the large test set, pseudolabeling was a great help. I got 73rd out of 2,245 participants, earning a silver medal. I wanted to share a few of my experiences, and I joined only 2 weeks before the end, and the competition had started 2 months prior. As a result, unlike the vast majority of participants and previous Kaggle winners, I did not have time to ensemble. I only had time to train one top-performing model and optimize it with a few of the techniques I've talked about. I used YOLO v4, which is an object detection model, along with augmentations such as cut mix, where parts of an image are cut out and pasted into a different image, hue, brightness, contrast, rotations, horizontal and vertical flips, and mosaic. So the model baseline performs around 0.69 intersection over union on the public leaderboard, higher is better, which was somewhere near the middle of the leaderboard, around 1,000th place. So this exact same model earned up to 22nd place on the private leaderboard. So there's a few steps to improve this model. Firstly, adding test time augmentation, or TTA. This means that the model infers on the same image multiple times, but with augmentations performed. So for example, as I said, we would infer once on the image, we'd rotate it, maybe change brightness, and then infer again on it. And so this would give us some better accuracy. This way, we had multiple images per output that we can ensemble. Then we used weighted boxes fusion to ensemble these outputs. With this TTA model, we have a score of about 0.7115 intersection over union on the public leaderboard with the exact same model. So this placed around 300th place on the private leaderboard. Finally, with TTA inference to pseudolabeling and adding out of fold, we got a score of 0.7406 on the public leaderboard, or 0.6225 on the private leaderboard. So this is an improvement of 4% purely with self-training, which practically was just copy and pasting some inference code and some training code. And so this would have boosted us to 36th place. And finally, if we added pre-training, I did this in late submissions, we would have scored 0.7562 on the public leaderboard, 61st place, and 22nd place on the private leaderboard. So this is where we would first train on the pseudo labels, and then we would fine tune on the label data. So essentially, with only this one model, we improved 5% by adding pre-training, boosting from 327th place to a possible 22nd place. All of the notebooks used to train these models are referenced in the GitHub link and open sourced if anyone's interested, though they're quite verbose. However, this is far from the only application in Kaggle competitions. These are just a few recent competitions in the past 6 months I picked out, and there's a wide variety of competitions in which these were applied. From our mRNA sequence prediction in the open vaccine competition, in which first, second, and third all used pseudolabelings, to tabular competitions, such as Harvard's method of action prediction, in which the first place used pseudolabeling as well as the fifth place, to trends neuroimaging, to NLP in the tweet sentiment classification, and of course, computer vision in the TGS salt identification challenge, which was a segmentation problem, and global wheat detection, which was a object detection challenge. Finally, let's talk about a real-world example of how pseudolabeling was used to make a record-breaking model. This model was the previous state-of-the-art on ImageNet until 2 months ago. ImageNet is a dataset of 14 million hand-labeled images from 1,000 classes designed to be a comprehensive evaluation metric. This model is currently tied for number 1 and is called EfficientNet L2 Noisy Student. The architecture is identical to the original EfficientNet paper from 2019, but performs 4% better in top 1 accuracy and 1.6% better in top 5 accuracy, purely from pseudolabeling. Noisy Student achieves this through a novel approach to pseudolabeling. Here's an extract from the paper. Noisy Student training extends the idea of self-training and distillation with the use of equal or larger student models and noise added to student during training. On ImageNet, we first train an EfficientNet model with labeled images and use it as a teacher to generate pseudolabels for 300 million unlabeled images. We then train a larger EfficientNet as a student model on the combination of labeled and pseudolabeled images. We iterate in this process by letting back the student as a teacher. During the learning as a student, we inject noise such as dropout, stochastic depth, random augment to the student so that the student generalizes better than the teacher. End quote. To put this into plainer English, they first use a small model, EfficientNet B7, which is trained on the labeled data. Then this model is turned into the teacher, used to infer on the 300 million images, and then produces pseudolabels again, combined with ImageNet labeled data to train the next largest model, an EfficientNet L0. Then the L0 turns into the teacher, teaches an L1, and this is iterated upon 5 times. Through augmentations and noise, the student model actually improves on the teacher. Techniques used include stochastic depth, where layers are dropped and the others are boosted as a shortcut. And this was introduced with the residual networks paper a few years ago, dropout, and random image augmentation. This way, the student model is not only larger and wider than the original teacher model, containing more data, but also more generalized due to the noise. The resulting model is more robust, performing not only better on ImageNet, but also against adversarial opponents. We can see in ImageNet A, C, and P that these images that are barely able for us to detect. Sorry about that. My apologies. ImageNet A, C, and P, for images that we can barely even see, it performs much better than the previous state-of-the-art EfficientNet. This performance is not really unique to the dataset it's trained on either. An identical dataset was used to train Big Transfer, BIT-L on this table, with 928 million parameters, more than double that of EfficientNet L2, yet it still only achieves 87.5% accuracy without this pre-training and soft pseudo-labeling scheme. A few other techniques are used that I mentioned. The inference of pseudo-labels uses TTA, and a quote from the paper mentions, "This way the student is forced to approximate what is essentially an ensemble." In addition, since the dataset isn't balanced, synthetic minority oversampling is used. So for example, if we have a lot of one class, we would oversample the least common class and then undersample the most common class. Finally, to end off, I have a bit of a minimal example in a notebook at this link on screen, bit.ly/PyData-notebook. So this is a very minimal example trained on MNIST dataset and TensorFlow, exploring some of the three methods I discussed today: self-training, simultaneous training, and pre-training. The cross-validation is just simple train test split, and there's no augmentations. The train set of MNIST is actually double the size of the test set, so this really isn't an ideal application, but I thought this would be a nice way to simply demonstrate the code. So we first have some basic data loading, and we define our model. So we first train our pseudo-labeling baseline, which performs about 99% on the MNIST test set. We can then try self-training. So we first load the weights of the baseline model, and then we produce pseudo-labels by predicting on the test set and then converting them. Then we can fine-tune on the test set, and finally we get an accuracy of about 99.1% accuracy. So a very small improvement, but still a tangible improvement. And then in simultaneous training, we first pseudo-label. So we load the previous baseline model, and then we combine all the test data and the train data together, and then we train on it, and the accuracy is identical to the original baseline. Finally, we can use pre-training. Again, we produce our pseudo-labels, and then we first train only on pseudo-labels, and then we can fine-tune on the label data, and this gives us a larger boost, 99.1% accuracy. And so, yeah, this is just a really minimal code example in which just with, I guess, 10 lines of code, we can switch from no pseudo-labeling to self-training to simultaneous training to pre-training. And the final difference between pseudo-labeling and self-training is 0.06%. Simultaneous training is actually a bit worse. And then pre-training is about 0.04% better. Extremely thin margins, but again, this is on MNIST, far from an ideal application. And in addition, we're already so close to 100% accuracy, it's difficult to improve. But yeah, just a very basic code baseline. Thank you all for attending my talk and sticking around till the end. And I hope I introduced the versatility and power of pseudo-labeling. I am looking for paid or unpaid remote internships in Alberta, Canada, or remote during the winter of 2020 or summer 2021. Please email me at szeng3@athabasca.edu or message me on LinkedIn, and I'd be happy to send over my resume. You can connect with me on LinkedIn, Kaggle, or GitHub at STANLEY ZHENG. Thanks again, stay safe, and happy holidays.
Thank you, Stanley, for your presentation. We already have some questions in the chat. Let's see. First one was from Mon on where will you not suggest using pseudo-labels? False negatives are sometimes lethal.
Yeah. So pseudo-labeling really accentuates a big class imbalance. So if you have a huge class imbalance, it's quite difficult to find a suitable pseudolabeling implementation. What else? That's all I can think of on the top of my head, but definitely class imbalance. And also, you likely won't see any you won't likely see any improvement if there's not a huge difference in the train and test sets, or if the train set's larger than the test set generally.
Right. And then Andy was wondering if pseudo-labeling and semi-supervised learning in general can even work efficiently on large-scale projects, such as detecting human trafficking.
Yeah, I think large-scale projects is somewhere this benefits a lot, but maybe not human trafficking in particular, because it sounds like that's not really a problem of labeling the data, which is really what semi-supervised learning is meant for. Human trafficking sounds like something which we would just be limited by data in general, right? So maybe not the best application. But yeah, just large-scale projects would be great. For example, the Facebook data set of over 300 million images was a really great example of pseudo-labeling. Anything else?
And then Ted just had a quick question about, for the global weak detection model, what was the unlabeled data used for it? Was it images or was it something else?
Yeah, so actually, we can go back to this. Share screen. Yeah, so global weak detection was just object detection. So it would just give us an additional, I guess, 2,000 images, which we can then pseudo-label. These are actually pseudo-labeled images. So we can just pseudo-label them and we can train on them additionally. If that answers the question. Just additional images to train on, yeah.
I think that's really all the questions people had.
I have a quick question if I can jump in. Stanley, great talk. Definitely learned a lot in this short amount of time, so well done. I have a question for you around how you perceive any type of like ethical challenges that comes with pseudo labeling. I think for perspective, so for instance, if the labels you have are then used to train on a data set where there could have been some systematic reason why the labels don't exist, do you think that that would cause some sort of introduced bias to the model? I'm coming from like a healthcare perspective, so I'm curious on like how you've thought about like ethical challenges or bias-based challenges.
Yeah, definitely. I'm not particularly, or not at all, an expert on bias or anything like that. I mainly just do competitions on Kaggle or freelancing work. So I'm not really too familiar with the bias, but definitely it is a very real possibility that if there was some real reason that some data was not labeled, then yeah, I do see some bias there. Yeah, sorry, I can't really answer that question too well.
No, I think this is like, it's always evolving questions. I think this is awesome. Gives me a lot more to think about, I think, moving forward from here. So definitely appreciate it.
Yep. My pleasure.
Great. Were there any other questions from the audience? I guess that's a wrap. Thank you so much, Stanley, again, for this presentation, and going to move on to Harini. We'll have her share her screen.
Awesome. Okay, can everyone see my screen?
I see it.
Awesome. Yeah, so hello everyone. My name is Harini Kannan. I'm a data scientist at Capsulate. It's a cybersecurity company based in New York City. And it basically provides protection for Linux enterprise infrastructure. So my job profile generally includes, all kinds of anomaly detection, and I generally work with data sets, systems related data sets like, process or network data or, file paths and all that. So that is a very quick introduction of what I do. And today's topic is topic modeling for data discovery. We're going to see a cybersecurity use case. Actually, Stanley's talk was great, was an awesome foundation for what we're going to see right now, because topic modeling is an unsupervised NLP approach, right? So yeah, so a very quick introduction on what kind of applied ML you see in cybersecurity. It can be basically broadly classified into two classes. Either you're going to be working in models that are defending against malicious activity, or you're going to be working, aiding the ethical hacking infrastructure and systems, aiding the attack mechanisms. So when you're defending against malicious activity, some of the examples of what kind of models we'd be doing, those are like, learning and detecting very, very specific kinds of attacks, right? So there are various exploits being released out there. I work specifically with the Linux related exploits. So, you're detecting specific kinds of attacks. That's one kind of work you generally do. The other one is user behavior analysis, like studying the user behavior or a developer behavior in Linux clusters, and developing models specifically for detecting the anomalies, the anomalous activity there. Or network analysis, this you see a lot of examples out there, detecting DGA and all kinds of network data that you can use to for anomaly detection. So that's one kind of use case. When you're aiding, when ML is used for aiding ethical hacking, right? You're basically doing that to strengthen, to harden your systems. So when you do that, some of the use cases include adversarial models to circumvent existing detections. Those could be ML detections, those could be deterministic detections, anything. You're basically working to working on attack models. Right, and then data poisoning, how you can circumvent existing ML models by introducing some way by poisoning the data, by poisoning the training data or something. That's an interesting field. What we are going to see today is relevant to the third point that has been highlighted, which is reconnaissance activity to capture leaked credentials. So you basically try and collect data and do analysis to figure out, can you find any leaked passwords and leaked credentials. This is generally done by, something called red teams. So in security teams in general, you have two, in penetration testing teams, right? You have two kinds of teams. Red team is the ethical hacking group, and blue team is the one that's going to defend against the red teams, right? So they simulate a lot of attack scenarios to make sure your company's infrastructure, your company's applications, everything is secure. So red team is basically a group of ethical hackers, right? So they do offensive security, they do ethical hacking, exploiting vulnerabilities, penetration testing, black box testing, social engineering. That's and all the attack stuff. And the blue team is the one that defends that. Blue team is the one that builds the defense mechanisms. So their work profile generally includes defensive security, infrastructure protection, damage control, incident response, analyzing all kinds of threat detection, threat hunting, digital forensics, and all that. So what we are going to see today is a methodology that would help speed up the data analysis part for the red teams. Right. So remember, we talked about reconnaissance, right? We want to go through huge data sets to find out interesting data points, like, leaked passwords or credentials or codes or whatever is there in like huge corpus of data. So the first step for our teams is information gathering. So they consist of ethical hackers, as we saw before. They evaluate system security in an objective manner. So once a target is set, right, meaning once they identify a specific part of the infrastructure or specific application to attack, the first step that they want to do is gather information on their attack target, right? So that information could be anything, depending on what kind of company they are working with, right? So it could be the names and phone numbers and email addresses and all that information within that organization. It could be social media accounts. It could be what kind of ports are open, where can you start getting the data, what kind of domain names, IP addresses that you see in the traffic, in the network traffic, right? And what kind of insecure files, programs, and is there any server misconfigurations that you can exploit? And they look for passwords, leaked passwords and credentials. That's the very first easiest step to get into systems and applications without even doing anything, right? So now we have a messy log data set. So they get their hands on huge number of logs. It could be from any number of systems, right? It could be from various system dumps. Most of them are unstructured data, right? So it's generally a problem of big data for them. So where do you start? This is one of the most time-consuming tasks for Red Team. We actually started this project after a Red Team member came to us saying, do you have any ML solution that you can apply that would speed up this process? Right. So yeah, their main goal was to recover leaked passwords. Also, we can argue that you can simply use filter using simple tools like grep or something to figure out whether you have useful data. But what do you grep on? You have this huge corpus of data and you don't know where to start with. So it's a classic NLP problem where we have unstructured data. We have data from multiple sources. We don't know where to start with. There's obviously no labels, and there's a lot of time there's no context. A red team suddenly jumps in, and then you get hold of this data. There's not a lot of context, or you have to spend time to learn that, right? So so this project is the one that introduced me to topic modeling. So I started exploring this only after knowing, okay, this is the problem. What are the ways to solve it? Right. So topic modeling was very interesting approach, and I tried it. And surprisingly, we could find a lot more leak credentials than what the red team member could find manually. So topic modeling is a statistical technique for discovering topics, right? Like clustered topics that occur in a collection of documents. It basically derives hidden patterns exhibited by text corpus. It's basically a form of document clustering, right? So where do you generally see topic modeling? If you simply Google topic modeling, the first thing that would come up is a New York Times example of using to boost their user article recommendation engines. You have tons of examples on that. Where they're clustering all the news articles into known topics like this is sports, this is politics, this is weather, etc. And then you see recruitment industries extract latent features of job descriptions and map them to the right candidates. In marketing, you see clustering the social media profiles. A lot of it is used for targeted marketing for the specific products, right? The place where it's actually a big deal, and I did not know this before specifically Googling for it, is it's used in search engine optimization. Google actually confirmed that they are using topic modeling to assist their ranking algorithm. And once the slide is shared, there's the link to the blog post from Google, and there's another paper there stating different other applications of topic modeling. Yeah. So the common techniques used for topic modeling is latent semantic analysis, probabilistic latent semantic analysis, and latent direct allocation. LSA is simply, it finds low dimension representation of documents and words. PLSA, the probabilistic latent semantic analysis, is instead of using matrices, it uses a probabilistic method. Right. LDA, which we are going to see today, and which is probably the most used one, is simply a generalized form of PLSA, but by changing the document index to a Dirichlet prior. Okay, so let's see the intuition behind LDA. We will not be going into a lot of the algorithm specific as to how it actually works. You have tons of literature on that if you want to learn about LDA, the mechanism, how the mechanics work behind the algorithm, and the theory behind it. But to understand the general intuition behind LDA, each document is considered as a collection of topics in a certain proportion. And each topic is a collection of keywords in a certain proportion. So basically, you want to find the dominant topic in each, dominant keywords in each topic. That's the goal of this, right? So once the number of topics is given to the algorithm, here that cannot be found automatically. We have to give it. So we'll also see how to figure out what's the optimum number of topics to give, right? So once the number of topics is given, it rearranges the topics distribution within the documents and keyword distribution, within the documents and the keyword distribution within the topics. So it's a topic document matrix and keyword topic matrix, right? To obtain a good composition of topic keywords distribution. Basically it backtracks and tries to figure out the topics which would create those documents in the first place. You'll understand it, I think, easier here. So it's a matrix factorization technique. If you see in the visualization here, right, any corpus is represented as a document term matrix here. So in the first matrix here, this shows a corpus of n documents, D1, D2, D3, with a vocabulary of m words, right? And then LDA converts this document term matrix into two lower dimensional matrices, M1 and M2. And then in the next two visualizations, next two matrices that you see, M1 is a document topic matrix with dimension n and k. M2 is a topic term matrix with dimension k and m. And n is the number of documents, k is the number of topics, and m is the vocabulary size. This could be confusing if this is suddenly put before you, but I promise you, if you go through the whole mechanics of how it works, it's simple to understand. So this is just to get an introduction before going to the actual application and the code, right? So for every topic, two probabilities are calculated, right? The first one is the proportion of words in a document that are currently assigned to a topic. The second one is the proportion of assignments to topic over all documents that come from this word. So finally, the current topic word assignment is updated with a new topic. This is done in iteration, right? With the probability product of P1 and P2. So once you iterate over this multiple times, the model finally reaches the convergence point, and the steady state is achieved when there is a good document topic or topic term distribution. Well, you can change it based on, once you have seen the topics and it's coherent, if it makes sense, it kind of works. So, okay, now let's get to the actual application. So we got hold of this nation state hackers' hard drives. This is a real scenario. A red team member came to us with the hard disk from a nation state hacker, and I was given access to the system logs in a single hard drive for analysis, right? So the challenge was the red team, they spent a lot of time to filter a few hundred passwords. So they were like, can you find out more than us? And can you do that in a fraction of time that which we did, right? So, okay, after a few slides, we will look at the code. But we have changed the data set because we cannot use the real data that's confidential, and we don't have permission to send it out. But the code remains the same. I simply changed the data set. Later, I'll show you the visualizations from the real data set by blacking out the passwords and stuff, but the methodology is the same, just the data is different, right? So step by step, we will go through the normal pre-processing that we do for any NLP project, right? So we prepare the stop words, we remove the unnecessary characters, we tokenize sentences and lematize, and then once we finish the pre-processing, we'll create a dictionary and corpus to be used for topic modeling, right? The stop words and everything would be slightly different from what we normally do with a normal English corpus, because your system corpus is going to be different. Your stop words for, say, if my data set is from Linux shell, right? My vocabulary is going to be different. It's going to be whatever shell commands that you type. If your data set is going to be network related data, your stop words is going to be different for that. So you can simply change based on whatever kind of corpus you have, right? Then you create the model, and then you have something called coherence scores, which you can use to figure out what's your optimum number of topics for your corpus, right? And then we do the model selection, we figure out what's the dominant topic in each document, and most representative sentence for each topic. It's optional. You figure out, you visualize the word cloud, you visualize t-SNE clustering, you visualize the model. We'll see all this later. So yeah, let me send the link. So yeah, I can send you the link of this. To the, okay, I don't think I can access the chat for some reason when I'm sharing.
Yeah, you might have to unshare and then put it in the chat.
Okay, yeah, okay, I just got it. I think you should be able to see this notebook. Yeah, so we saw what a topic is and what LDA is and everything, right? So we will go to what we are doing in this notebook, right? So obviously I was not able to share the real data. So what I've done is we have a TCP dump data. It's a network data set from a cybersecurity defense competition where the teams were physically co-located in the same building. Each team was given physically identical computer configurations. Throughout the competition, the teams had to ensure that the systems supply the specified services while under attack. So there was a volunteer red team that was doing the attack. And in addition, the teams had to satisfy periodic injects that simulate, business activities that looked real, like in real world. Right. So also note, this is a huge data set. So if you, I tried bringing the whole data set into Collab and it kind of crashed. So maybe try this in your own environment, or maybe reduce the data set size. So our task, this also contains passwords. This may look trivial, I mean, for this data, but in real world where you don't know whether you have passwords or anything out there, it would be interesting. But this is a useful use case to replicate the same experiment, right? So we are going to build a LDA model, and let's see. So so this is basically, so yeah, here if you see how to, so you download the data set from this link here. It would be a PCAP data set, .pcap, right? So the easiest way I found was just open the data set in Wireshark. It's a network application, and then you can export it as CSV. For the purposes of running this notebook, I randomly took like 100,000 data points to run this faster. Right, so we are going to use Gensim for the LDA model, right? So the raw data look like this, right? You have the source, the destination, the what's the protocol, and then you have the actual information that you want to look at. So here you have the pre-processing steps. The pre-processing steps go through, the normal steps here, like, using the stop words. So this assumes that you are familiar with the basics of NLP, right? The pre-processing and stuff. If not, I think this should give you a start, like a jump start to, just start Googling like what's stop words, what's lemmatization, what's everything, and this should give you a jump start, I think. So just a quick intro. Stop words are like, common words in a corpus that you don't want, like that are of little value for the documents matching. So also, other than English language, consider domain-specific stop words. Like it could be different for Linux data set, it could be different for network data set, and all that. Lemmatization we are doing here, that is grouping together, different inflected forms of a word so they can be analyzed as a single item, right? It brings context to the words. It links words with similar meaning to one word. For example, better and good, it will have the same context. Corpora, corpus, has the same context. Rocks, rock, has the same context, right? So those kinds of pre-processing you would do, and yeah, you're creating the bigrams, the trigrams, and all that. So once that's done, you have your corpus ready, right? So once you have the corpus ready, let's build a model. So for building the model, while building the model, we are actually going to build multiple models and calculate coherence value. So to give you a quick intro of what coherence value means, you basically evaluate a topic model using coherence value. It assures the quality of the learned topics, right? Whether it's coherent or it just, it simply doesn't make sense. So it does that by measuring the relative distance between words within a topic. So higher the score, better the model, right? So we did that, and then we are computing the coherence values. The code, everything is here, is in here. You can, test it out. And then we are plotting the coherence values for all the different models that we have calculated with different number of topics. Obviously, it's spiking the most for 5 number of topics, right? Doesn't necessarily mean that is the best model that you have. So you can probably experiment it with, say, experiment with 5 and then experiment with 7, and then see whether dividing that into, more number of topics maybe could give you from a human introspection that, that's a better topic. So yeah, so here for just for experiment purposes, I've just taken the highest coherence values model, right? And I'm looking at the top words, the keywords in that model, right, for each topic. And then you have that, and then you see what's the dominant topic in each document and the topic weight, right? And then you see for each topic you have what are the keywords that the model has produced. And then you see the word cloud. for the topics, you can see here it's coherent enough. Like you can see here, topic 1 has, pass, it has user somewhere. It would be clearer here, I think. Yeah, topic 1 has pass, that could be password, right? And it has user, it has membership, it has unknown, so error, so that could be authentication stuff related. So okay, now we see this is an interesting topic that I would like to explore. So let's go and explore further. So given a huge corpus of data where you simply don't know what's the context behind it, this is a very useful way to in an unsupervised way, simply cluster them into different groups, right, into different topics. Now, another way to visualize this and then classify them is using TSNE, right? TSNE is a dimension reduction technique. You'd be familiar with the PCA, the principal component analysis, right? That's the linear dimension reduction technique. TSNE is similar one. It's called T-distributed stochastic neighbor embedding. It's a tool to, again, similar to PCA, visualize high dimensional data. I use it a lot, especially in InfoSec. It's very useful. It's very important to be for a model to be as explainable as possible, right? Like if you have a result, people will definitely ask you, why do you have this? Why do you think this data point is neighbor to that data point? So it's always, so TSNE is a very, very useful tool. It maps multidimensional data to 2 or more dimensions suitable for human observation. It converts similarities between data points to joint probabilities, right? So you can, classify it by different topics, and then later in the slides, I'll show you the actual TSNE of the hacker data set which is very interesting. And then you use PyLDA with library, which is a Python wrapper over LDA, which is a very, I think, well-known OR library, which you can, visualize it and then go and filter for, which topic you want. So this is a useful visualization too. So here it's very simplistically, it gives the passwords, but in real data, but it actually makes sense that here also it proves the our hypothesis that all the passwords are grouped into one topic, and then how much ever big it is, you just find all whatever credentials that are leaked, right? So okay, so let's go back to this. And right, so this is from the real hacker dataset, right? You can see topic 3 has password, save, login, cloud backup, access, all that blah, 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 which clearly shows, okay, so this is a topic that you could go and look more into, right? And topic 0 is, you can see, verify account, verification, code, mobile, all that. Okay, so this is some kind of a topic that shows like, codes. So that's an interesting topic to see. So topic 3 exposes the keyword password. So we know that's a good starting point. Here you can see we just go and go and look at that particular thing, and you actually have the real passwords. So we kind of logged it up, and the real link to which that password is used. So yeah, the one that they took a lot of time to actually go and finally catch it in, a specific document in hundreds of documents. You get it basically in few seconds or minutes. right? Topic 0 was interesting. Go and look for verification, and it was for WeChat, I think. It was all the verification codes for that particular application for some reason that was stored. So yeah, so this was the T-SNE plot for the hacker data set, which was very interesting because it had a very nice structure to when you visualize the data, right? So yeah, that is basically it. Hopefully this will if you already are familiar with topic modeling, I think you actually know more than me. So and if not, I think this notebook should give you a jump start to topic modeling, to not just this data set or any kind of data set that you want. And yeah, hopefully this would also interest you in cybersecurity as a domain for experimenting in developing your ML endeavors. Yeah.
Great, thank you so much, Harini. So there were a few questions from the audience, one of which came from Mon about why is T-SNE preferred over UMAP in information security?
I'm actually not sure. I have generally used T-SNE and PCA because PCA is pretty fast, and then T-SNE, if you don't have a large number of features, then T-SNE was generally better. I have not used UMAP, so I don't have the answer for that, but that's a very good question to ponder over, I guess. I generally use PCA if there's a huge feature set, and T-SNE if otherwise, but that is interesting. And thank you for bringing it up. I think it's a good question to ponder, I mean, to research.
And have you?
I'm not sure whether UMAP, I mean, is the preferred. I mean, T-SNE is preferred over UMAP in InfoSec. I mean, that's really my bias. It could be completely different outside. I'm not sure.
Great. One other question was, have you ever encountered a false positive where the learning model says that there is a correlation between something and it actually wasn't?
Oh, all the time. Yeah. I mean, right. So one of the biggest challenges in InfoSec, cybersecurity in general, especially, I saw the difference from how different it is from the data sets that you generally use in, like, in your academia, in your masters and everything, versus coming to the industry. There was simply no labels. There was simply no labels, and it was so expensive to actually get labeled data, especially in cybersecurity, because getting attack labels is very expensive. You either have a honeypot or something to, you have to maintain that to get attackers in the wild to come and attack the system. So you can have labeled data, or your company generally has to spend a lot to actually simulate that environment, right? So so most of my experiments right from my internship has always been unsupervised. So with that, you obviously have a huge amount of false positives, and the trick is to figure out the trick is in feature engineering, is what I've seen so far, in terms of, you have all these security experts who know much more than me as a data scientist, in terms of what kind of features you can use or you can engineer that would make your model better. But false positives is one of the biggest pain point in cybersecurity. And also, compared to other domains, like in ad tech or somewhere where your model accuracy could be 90%, 95%, and it could go into production, whereas in cybersecurity the threshold is really, really high. It has to be like 99.7%, 99.8% to actually even be considered for production.
Great. I think those are all the questions in the chat. I was wondering if anyone else in the audience want to chime in with a question.
I have a question. Harini, again, another great talk. I think this was fabulous. I learned a lot, in the short time. And my question for you, coming from like the cybersecurity space, and I'm just thinking back to even, I think it's last week that the FireEye hack that happened based on like a password, SolarWinds123.
Right, the SolarWinds, yeah.
So to me, I'm just like, all right, simple passwords, and like, what are the things that we need to be doing to kind of protect that? From my question to you is, from your perspective, how much do you see kind of machine learning, NLP really supporting the cybersecurity space, especially as all this automation comes into play with like DevOps, InfoSec, and so there's a lot less humans in the loop. So kind of where do you see things going the next few years on the ML and cybersecurity space?
Right. It's actually a great question. And I have been talking about this like within my company or within the InfoSec community for a while, which is ML and InfoSec has not reached a stage, or definitely lagging behind how much the ML has progressed in other domains, right? And a lot of it has been because of a lot of companies touting normal blacklists or whitelists as ML. So the term itself is kind of tainted a little bit. As far as, having said that, now there's a lot of development because of awareness being created in all these conferences. Black Hat had their first AI and ML separate section in their conference. Black Hat is one of the biggest or the most premier conference that you have in cybersecurity. It has been running for 20-21 years. And I was lucky enough to give a talk this year. This was the first time AI and ML got added. So a lot of people are talking about it, or talking about, a lot of work is going on in adversarial ML, like especially data poisoning and all that, and how, given existing models, how can you circumvent them? There's a lot of work going on in there. And one of the biggest places where work is going on is for reducing the alert fatigue, reducing the false positives. Even without AI and ML, right? One of the biggest problems in cybersecurity is having false positives, even from non-stochastic, deterministic detections. People go through that, security analysts go through that manually, which is a pain. So, which is one of the areas where ML can help, in clustering out, filtering out all the false positives, which they're working on. And so I think there's a lot of development going on there. And I have been specifically working on, performance counter related data, which is like, has surprisingly not been researched or touched a lot from ML side. Like you have tons of data in terms of what your system is generating in terms of performance counters, right? The Intel counters that are continuously giving out data. There's so much of data available, and not much research done there, especially with the Spectrum meltdown that came out last year. Not last year, 2018, I think. So yeah, it's definitely catching up. People are noticing it. Obviously, would love so many more people to come into cybersecurity, and look that as a domain. I mean, be it in in college or while we're starting the ML journey, right? Like I never thought I would get into cybersecurity, but yeah, it's a pretty cool field. Like if yeah, we definitely need more people, more ML people there.
Great. Is there anyone else with last thoughts or Last question. Stanley wrote, great talk, Harini. Didn't realize machine learning played such a large part in cybersecurity. So I'm glad various people, various attendees here mentioned learning a bit from both of your presentations and have expressed thanks for both of your thought-provoking presentations as well. So thank you, Stanley. Thank you, Harini. Thank you all the attendees for joining us for this last event of the year. And we'll post links shared tonight on any additional follow-ups in our Slack channel and PyData Boston. And please stay posted on PyData Boston's events and Meetup. With that, I just want to wish everyone happy holidays, and we hope to see you next year.
Thank you. Happy holidays.
Happy holidays, everyone.